Okay, in section 5.5, there's two theorems that we got to talk about, and then we'll finally be done with chapter 5. So in 5.3, when we solved polynomial equations and found their roots, this section is relating theorems about those roots. And so we're actually going to kind of work backwards in a sense today. There's some things that are true about polynomial roots. The first theorem we're going to look at is called the conjugate root theorem. Okay, this theorem says if you have either irrational or complex roots, irrational or complex roots, they occur in conjugate pairs. Irrational or complex roots, they occur in conjugate pairs. Whole numbers and fractions do not. Yes. Sure. Let me toss it to you. Okay. There you go.
Thank you.
You're welcome. All right, so they occur in conjugate pairs. Now let's back up and let's remember what an irrational number looks like, complex number, and then we'll talk about what conjugates look like to help us make sense of this. An irrational number is in the form of like pi, square root of 2, square root of 7. It's any type of number that repeats, that does not repeat, but it goes on forever. So like if you type in pi, of course it's like 3.141628, and it keeps on going, but there's no repeating pattern to it. Same thing with square root of 2, square root of 7, square root of 15, numbers that you can't take the square root of and get a whole number answer. So those are like irrational numbers. Complex numbers, so like root 2, root 7, so on. Complex numbers are in the form a plus bi. Remember us studying about complex numbers in section 4.8. Complex numbers have I, that imaginary number, in them. Okay, now to talk about conjugate pairs. Conjugate simply means if I've got, like for example, x plus 5, its conjugate pair is going to be x minus 5. So you're going to have the same terms, x and 5, but the sign separating them is different. So if I've got a squared plus root 7, what is its conjugate pair? It would be a squared what? Minus root 7. It'd be a squared minus root 7. I didn't hear what you said. I'm sorry. What'd you say? Oh, okay. Root 7, yeah, is part of it. Okay, so what this theorem simply says, if I've got something that looks like an irrational, this is what an irrational root will look like. You might have 1 plus root 7. If it tells you that 1 plus root 7 is a root of a polynomial, you can assume and know that 1 minus root 7 is also a root. If it tells you that negative 6i is a root of a polynomial, you can also assume its conjugate pair, which is positive 6i, is also a root. So some of your Math Excel, or one or two of your Math Excel problems, are simply going to ask you list however many other roots. And they may give you 1 plus root 7, so you would type in 1 minus root 7. So it's as easy as that. We'll look at those. Let's say they give you something like 1/2 plus 4i. That's a complex root. You can also know that 1/2 minus 4i is also a root. So that's all it means by conjugate root. They have to occur in pairs, irrational and complex. All right, so your directions are all kind of different in 5.5. This one says find 2 other roots, type them in separated by comma, for polynomial p of x. And they give you that 10 plus root 3 is a root. And they also tell you that negative 4i is a root. So based on what you know, tell me what's this root's conjugate pair. What other root will you have? Good, 10 minus root 3. And then what about here? Good, 4i. Y'all okay with that? The next type of problem that deals with that, it will actually ask you find the polynomial equation p of x that has the roots given. Now, it also may say like real coefficients. So find a polynomial equation with real coefficients. That simply means that you're going to have like whole numbers or fractions in front of x squared and x cubed and all that. So find the polynomial equation with real coefficients that has the roots, and this is what you're given. 1 and negative 6i. So they give you root 1 and root negative 6i. So the first thing that you have to do is determine if you have any other roots. And based on this complex root, we know that what is also a root? 6i. But whole numbers, fractions, decimals, none of those have root pairs. So 1 is just a root by itself. Okay, how you're like, this is why I said we're working backwards. These are actually your answers that you would get if you solve the polynomial equation that's actually gonna become our answer. You take these roots and you put them back in factored form. So the way you do that is you just say x is always in the front, and you do the opposite of it. So the opposite of positive 1 is negative 1. So remember when we were solving in 5.3, I said you factor it, then you set each factor equal to 0. So if I were to solve this part, I would get 1. Then here, you do the same thing. This is minus or negative 6i, so you're going to say plus 6i. And then at the end, that's positive 6i, so we put minus 6i. You always want, so from here, what we're going to do is have to multiply all of this out. You always want to multiply your complex numbers together first, because your i's should all cancel out and you'll be left with prettier numbers. So I'm going to not worry about x minus 1 for this step, and let's focus on multiplying x plus 6i times x minus 6i. And you don't have to write it again. Okay, when we do the FOIL method or distribute x times x, you're going to get x squared. When you take x and multiply it to negative 6i, negative xi. Take positive 6i and multiply it to x. And take 6i and multiply it to negative 6i. So that gives you negative 36i squared. Do you guys remember in 4.8, what was I squared equal to? I squared turns into something. Good, it turns into negative 1. Okay, so notice that this negative 6i, positive 6i cancel, and that's what you want. You're left with x squared. Then this becomes negative 36 times negative 1. I squared is simply going to change the sign of the number in front and go away. So negative 36i squared becomes positive 36. All right, but we still had the x minus 1 that was out front that we can't forget. So we have to multiply that to x squared plus 36, and then we'll be done. Okay, go through the same process, make sure you distribute. So x times x squared gives you x to the third. X times 36 is 36x. Negative 1 times x, negative x squared. Negative 1 times 36 minus 36. Okay, the only thing that, like, once you've multiplied everything together, make sure that you don't have any like terms you can combine, and you don't. They may ask you to write it in standard form where you put your exponents in decreasing order, but this is your polynomial. So in 5.3, remember we started with this and we would factor it and work backwards, or well, we'd factor it and work to get these answers, which we really didn't arrive too many complex often. Are y'all okay with that? Yes. What'd you say? Yeah, yes. Which I'm okay, like, all you need to make sure, I think they give you boxes in Math Excel. Like, they'll give you a box in front of X, so you'll just have to type in like 36, and they'll give you a box in front of X squared, so you type in negative 1, I think, in most cases. As long as you get to this point, you're good. Try not to stress, because I know it's overwhelming anyway. All right. You still need that? Are you good? Okay. All right, this is number 9 in Math Excel. Definitely the hardest type that deals with the conjugate root theorem. And it works slightly differently than what we just did, because they give, instead of being given that like 3 is a root or 3i is a root, they give it to you in this form. They tell you that 1 minus root 3 is a root. They also go ahead and tell you that its conjugate pair, 1 plus root 3, is a root. Then they tell you that 7 minus I is a root. If you know that 7 minus I is a root, then what else is? 7 plus I. Okay, notice in that last problem that we did, you had 3 roots, and we ended up with a polynomial that had a degree of 3. This time we have 4 roots, so when we get to the end, we should have x to the 4th is our highest power. All right, what you're going to do, since they give you your roots with multiple terms or 2 terms, you're going to write them like this. Let me make sure I leave myself plenty of room. Try to, and you might have to write small because leave yourself plenty of room. All right, so I'm going to start out to this side. So for this first one, you're going to say x minus, and then you're going to put that root inside. And I'll show you when we do this way in a minute. And then times. The next one, you're also going to say x minus, and you're going to put this root inside. Okay, before we do the last two, let me kind of explain to you why we do that. You've got to remember that your factors actually have to be the opposite. So if I'm saying the opposite of 1 minus root 3, then this is how you actually show it in my form. The opposite of 1 minus root 3. And then you've got to also do, when you put this in factored form, the opposite of it. So the opposite of 1 plus root 3. When you do the last two, you do the same thing, x, and then I'll say the opposite of this factor 7 minus I. And then same thing at the end, x minus, for the opposite, 7 plus I. Okay, now before we multiply, let's go inside and distribute those minus signs. So here you're going to be left with x minus 1 plus root 3. All right, and then from here, you're going to be left with x minus 1 minus root 3. And then at the end, x minus 7 plus I. And x minus 7 minus I. Okay, is everybody okay up to that point? All right. Now, notice in each set, there's nothing you can combine. There's no like terms. So what I suggest you do is focus on multiplying the things that contain those radicals together, multiplying the things that contain your i's together, then finally multiplying those two answers. So that's the way we're going to treat it. Because if you multiply this that contains a radical to something that contains an I, you're going to have some pretty nasty stuff to deal with. So always multiply conjugate pairs together because things should cancel out. That's why they're conjugate pairs. So I tell you what, let's focus on I'm just going to rewrite it. You don't have to. I'm going to multiply the two things that have radicals together first. All right, so we're going to look at that. And then we can't forget that we still have this to do in a minute. You've got three things inside each parenthesis. So you have to make sure that you completely distribute everything. So multiply x to x to -1 and to -√3. And that's going to give you x squared. Then x times -1 gives you -x. X times -√3 is -√3, and x outside that radical. Okay, same thing with -1. Make sure you multiply it to x. -1 times -1. -1 times -√3. So that becomes +√3. All right, now you have to make sure you distribute +√3. So √3 times x. √3 times -1. And +√3 times -√3, -3. Whenever you multiply same radical to itself, your radicals cancel. Okay, some things should cancel out in this. Notice that your -√3x will cancel with that, +√3x. √3 cancels with -√3. And that's really what you want. If all of your radical stuff doesn't cancel, then you've done something wrong. Now let's combine like terms. We have x squared, and then minus x will give you -2x. And then 1 minus 3 is -2. So that definitely looks a lot better than x minus 1 plus √3. Okay, so that's our answer from multiplying the first two things. So put a star by that or something. You'll need that in a minute. All right, let's look at multiplying x minus 7 plus I, x minus 7 minus I. All right, same thing. Make sure you've got three terms, so make sure you multiply all. So x times x. X times -7. X times -I. Multiply -7 to x. Multiply -7 to -7. Multiply -7 to -I, so you get +7I. Okay, last thing, multiply I to x. Multiply I to -7. and then multiply I to negative I, so that's going to give you a negative I squared at the end. I can't put it on there. All right, let's go through. If we did everything correctly, everything with an I should cancel out. Notice that your 7i's, 7i minus 7i, that cancels. Then your xi, those both cancel. You can combine negative 7x and negative 7x. And I squared turns into what? What does negative I squared turn into? So if I go ahead and combine negative 7x, I get negative 14x. And then plus 49. And then negative I squared is going to turn into positive 1. Because remember, I squared was negative 1. All right, so last but not least, when we combine those like terms, you get this. So x squared minus 14x plus 50. Okay. Yeah, go ahead. All right. Multiply these together and we're finally done with this problem. All right, let's distribute x squared to all three terms. So x squared times x squared. It's going to give you x to the fourth. X squared times negative 14x, negative 14x to the third. X squared times 50, 50x squared. Okay, now we've got negative 2x to distribute. So negative 2x times x squared, negative 2x to the third. Negative 2x times negative 14x, positive 28x squared. Negative 2x times positive 50, negative 100x. I'm going to have to bring this down to the next line because we still have to distribute negative 2. So minus 2x squared. Negative 2 times negative 14x, positive 28x. Negative 2 times positive 50 is negative 100. And all we have to do now is combine any like terms. So negative 14x cubed minus 2x cubed, negative 16x cubed. $50x squared plus 28x squared, 78x squared, and then minus 2 more, so 76. And then we have negative 100x plus 28, negative 72x. And then minus 100. Everything's been combined. And I told you when we started that we should wind up with a degree of 4. So my highest exponent is 4. Hey, I like that one. It's terrible, huh? I thought about taking that one off your homework, but then it's good practice too. I don't know, I may still drop it. Bless you. How far do you have? You sure? Okay. Okay, our next theorem is not as terrible as that one. So last theorem of the day is rational roots theorem. So let's say that you've got a polynomial that will not factor. You can't factor it by grouping. It's not quadratic, so we can't use quadratic formula to solve it. Then this is the way that you do it. But we're going to save actually solving on using this method for pre-cal. All right, so rational roots theorem says that you can take the factors of your constant term and put them all over the factors of your leading coefficient the factors of your constant term over the factors of your leading coefficient, and you can, and it's positive and negative. You're going to consider both the positive and the negative. So let's say that positive 2 is a possible root of a polynomial, then negative 2 is considered to be a possible root. Doesn't mean that they actually are roots of the polynomial. Just means that they're possibly are. And then the process you would take after you find all of these possible roots is you would start plugging each of them in with a calculator to see which one gives you 0. So before you actually do this, you always need to make sure that your polynomial is in standard form and set equal to 0. Polynomial is in standard form and equal to 0. Find all possible roots of polynomial p of x and they give you p of x equals x squared plus 5x plus 2. So as long as your polynomial they give you is in standard form and everything is on one side of the equal sign from P of X, and it is, you can simply just set it equal to 0. Like if I set that equal to 0, then that's what I have. It's in standard form, it's set equal to 0, so I can find the possible roots that might work. Of course, this is quadratic. My highest exponent is 2, meaning it's quadratic. You could factor it or use the quadratic formula to actually get the roots that will work. But let's say that it wasn't quadratic and you couldn't do that. What is your constant term? What's the number at the end by itself? 2. So your constant is 2. You list all of the factors of it. What are all the factors of 2? What are the only 2 factors of 2? There you go. So 1 and 2 are my factors. What's your leading coefficient? Your degree is 2, so this is your leading term. What's the number in front of it? Leading coefficient is 1. And of course, the only factors of 1 is 1. So it started you off really with a very simple one. Your constant is 2, so it only has 2 factors, 1 in itself. And yes, you always list 1 as a factor. And then my leading coefficient is 1, so my only factor is 1. This is how you list all of your possible roots. You take your constant factors, which are 1 and 2, and you put them over your leading coefficient factors. So I'm going to say, and you're going to put positive, negative. So positive, negative. And then we say 1, the first factor of my constant, over 1, factor of my leading coefficient. Then I take my next factor, which is 2, and I set it over my factor of my coefficient 1. And of course, you can simplify that. So that'll just be positive, negative 1. That'll be positive, negative 2. And the reason that they call it rational roots theorem is because when you do this, you're either going to get whole numbers like we did, or you're going to be left with fractions. And that's the numbers that make up the rational system, is whole numbers and fractions. All right, we're going to do the same thing in 4. Find all your possible roots. And in this case, you're given that your polynomial is 14x to the 4th minus x squared plus 4. Okay, what's your constant? Okay, your constant is 4. So let's list all the factors of 4. What are all the factors of 4? 1, 2, and 4. What is your leading coefficient? Good. 14. So leading coefficient is 14. What are the factors of 14? 1, 2, 7, and 14. Okay, now you take every factor of your constant, 1, 2, and 4, and you have to set each one over every single one of these factors of your leading coefficient. So like I'm going to take 1 and set it over 1, Take 1 and set it over 2. 1 and set it over 7. 1 set it over 14. And of course, all of them are positive and negative. You do the same thing with 2. Take 2, set it over 1. Take 2, set it over 2. 2, set it over 7, and set it over 14. I'll go ahead and tell you, like, however many constant factors you have, multiply that by however many leading coefficients factors you have, and then that'll be your total possible roots that you should have in all. Like if I, of course, multiply 3 by 4, I'm going to have 12. All right, last but not least, do the same thing with 4. So positive, negative 4 over 1, positive, negative 4 over 2, 4 over 7, and 4 over 14. Okay, you need to make sure that it is simplified, like everything is simplified, and definitely do not type in anything that repeats. Like you don't have to type in 2 twice if it repeats. So I've got positive, negative 1, positive, negative 1/2, positive, negative 1/7, positive, negative 1/14, positive, negative 2. See, here I get 1 again, so I don't have to write it again. Positive, negative 2/7. And 2/14 reduces to what? 1/7, and you've already listed that, so you don't have to write that again. And then positive, negative 4. 4 over 2 reduces to 2, and you've already written that. And then positive, negative 4/7. And then 4 over 14 reduces to 2/7, and we've already written that. Now, we listed 12 in all, but they may reduce down, like some of these, of course, are the same possible root. All right, that's one of your hardest ones you'll have, is where you, of course, have a lot to deal with. What we're going to do in pre-cal next year is we would start, once we get simplified to this point, you would start plugging in positive, negative 1 into your equation to see which one would give you 0 as an answer and work. That means that that number would be a root. Then you would synthetically divide it by that number to get it broken down into an x cubed, and then you'd keep going. So it's pretty terrible process. But this is all we're doing for the day. All right, do you have any questions about that? All right. Work on your 5-5 math Excel. What? Oh, okay, sorry, me. Yeah, go ahead. Is it not letting you in, or is it telling you your account has expired, or you just do not remember?
Password.
Okay.
It was like program.